The whole reason for this prototype, what you guys have seen in the past month is a prototype. We didn't know it was going to work or not. And Victoria and I were discussing this back in the fall. It'd be a great idea to do this, to bring alumni back and show what they do, especially recent alumni, not people who have been gone for 20 years, because who cares? So it came to me when I saw Eric's talk at Wayne State in October of last year, wasn't it? Mm-hmm. Up in Detroit. And so when I heard his talk, I realized, holy crap, this is an amazing stuff that he's doing. We should have TU hear this somehow, find a vehicle for it to happen. And so Victoria was kind enough to listen to my ideas, and we made it happen as a prototype. And we met with different people in different parts of administration, and they said, okay, we should have this happen every week. I said, we can't do it every week now. I don't have enough people. Well, let's just test it, see what happens. So that's what we have. So Eric's the last of the four for the prototype. And I think based upon your reaction, I think we should have this in the fall. I think it's critical. And also when we were there, I called up Emma. I was sitting next to Eric, and I said, Emma, Eric, a student of mine has an idea about what happens to a drug in a maggot when it turns into a fly. Remember, we're sitting there before your talk in the lobby. And so I said, can you analyze that? And he said, sure. I'm like, oh, really? You can analyze a maggot and a fly? He goes, yeah, all I have to do is blah, 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 blah. I'm like going, perfect. So I texted Emma that same day and said, we can do this. He says, great. So the whole poster idea is going to be presented next week at the toxicology conference in Columbus is based upon that conversation that happened that day when I went to your fourth year talk. So a lot of things happened for that, but the critical thing is to hear what our graduates are doing either in grad school or their careers, as you've seen this whole time. So Dr. Davis, soon to be, by December, will getting his PhD in bioanalytical chemistry with a background in mass spectrometry and bioinformatics. He was a 2014 graduate from TU in general science. Remember the general science degree? Yeah. Remember that? In general science, not forensic science. There was no BS back then. We didn't have the BS degree until 2016. This was 2014. So he was just a BS in general science and behavioral science back then. Also a starting defensive lineman for TU under Coach Goff. So he's a defensive lineman. He was an excellent defensive lineman. He came from Northern Michigan, right? University of before that, yeah. His bio courses at TU, most of them were taken in Northern Michigan, but his bio courses at TU were lifespan development. Remember Anatomy 310 or 301 or whatever it was before we changed it? We had that one nurse teach it and everyone was up in arms about it.
That was before I did.
Yes.
Then I started out.
Exactly. So he came through that. Now I had Goshi. Wasn't it Goshi?
Yeah.
I don't know.
Who was the teacher?
I had you, Dr. Gosh, so I don't know.
There was somebody in the original one, though. Remember, we had, anyways, I don't want to go into details. So he also had survey of health and survey of science back then. But in chemistry courses, he had Gen Chem 1 and 2 with me.
John Miller's wife.
Who?
John Miller.
Okay.
She was a nurse.
Okay. So we had Gen Chem 1 and 2, organic 1 and 2. Quant, before it was analytical, we called it quantitative analysis, and then instrumental analysis without instruments. Again, this is in 2013, and biochem. So, and I taught all those classes and we had one lab, the lab that I'm in right now, the bio lab only had 2 benches. And if you notice, there is yellow tape on the middle of those benches. You notice that? Only the 2 have yellow tape. The reason for that is, if you notice, those benches only have 1 sink at the far end. We had to do organic distillations. You can't do that with just 1 sink. So in 2011, I got some piping from Lowe's and put plastic piping from that sink down to the far end, then back down as a drain to run distillation columns off of both those benches. And I had them cornered off in yellow tape. So everybody had their little section with their inlet and outlet.
He's leaving out a part too, that it was just a garage.
It was a garage.
It was a garage, like someone's garage where they parked their car. It was a garage.
It was horrific. I mean, we actually had a lab in that class. Anyways, that's when it started. That's why you see the yellow tape in there, because we had to do that. There's only 1 sink of those benches. So when we designed the new lab next door, I made sure we had benches with the actual sinks and everything else. So you see that in the third bench in that lab, because we added that 3rd bench. There was no 3rd bench there. Dr. Gosh's room is where I have the lab coats in right now. That was her office. The new lab is where we had Herlick and I had our own office with turtles.
Oh, you were in the passage.
Yeah. And we had one bathroom. We had,
That part of it was the garage where we started.
right. It was just, and we had labs in there. Anyways, once he got out of TU in 2014, he worked for a year at a bakery manufacturing plant as a chemical technician. And just share that story one time when you get started about when you were in Lansing in the state capitol, and that one person was at her desk looking at mass spec.
Oh yeah.
You got to share that story. It's hilarious. He was drafted and played football for the Montreal Alouettes in CFL. Also Western Michigan Ironman for the Arena League. He started at 2018 at Wayne State when he was a TA. And I told him back then, I says, you can go to grad school for free and they'll pay you to go to grad school and they'll pay you a stipend. He didn't believe me. He said, no way. I said, they'll pay you and they'll pay you a stipend because you can speak the language and you know chemistry. And he did at Wayne State. He's a TA for a year, getting paid to teach and a stipend to pay for his tuition. Then he was so good at research that he put him on a research fellowship, but no longer teaching anymore. So he devoted all his time to research and not teaching anymore. I have visited him several times, seen his mass spec lab, which is phenomenal. They have 17 operating mass spec units in the basement floor, office, building, room. They have a chemistry building. 5 floors? 4. 4, with 17 operating mass specs in the basement.
And that's just in the basement.
Yeah, and I've seen that one. I visited several times. I saw his 4th year talk, most recently in October, to a packed auditorium full of professors and grad students. His research is sickle cell anemia and Plasmodium falciparum, which is also known as malaria, not until now. And you will be amazed when you see his research. I bring to you Dr. Davis.
I'm not doctor yet. Hopefully in December I'll be one, but yeah, Eric Davis. I graduated from Airlines in 2014. I played football here. So just the story he's talking about with the whole like medical at the government building.
Yeah. Go ahead.
So at the government building, I can change it back to you.
Okay. Oh, you got it? Okay, cool.
So what that story was, when I wasn't, playing football, I would get cut and I would have to come home and I needed a job. So I was doing security at the state building in Grand Rapids. So there would always be a lady on the 5th floor, and the 5th floor was the kind of like the FDA, like the wildlife and stuff like that. So I remember I'm doing my rounds, I got a flashlight, and she's sitting there and she's looking at like these chemical compounds. And so I look over the desk and I go, I think something, I was like, that's this, and that. She's like, what? So she looks at me and goes, what you say? I'm like, that's this, that matches that, that's this chemical. And she looks at me and she goes, what? And so I say it again. She's like, how do you know that? I was like, I graduated from Tip University, this and that. So she pulls out more kind of like, she pulls out actually mass spec spectra, and she pulls out other like chemical compounds, and I'm giving the chemical names, and I'm like, yeah, this probably shouldn't be in your water, this and that. And she looks at me like, who are you? and I'm just like, I'm Eric Davis. She's like, show me some more. I'm talking to her, telling her this. She's like, how do you know this? And I'm looking at her like, what do you mean, how do I know this? So she keeps going.
Hang on, remember, this is a security guard in a government building.
Yes,
with a flashlight, a name badge, and a uniform.
Yeah. So I'm just sitting there doing that. And then she asked me more questions. I'm answering them. And she's like, how do you know this? And she says that about 3 times. I'm just like, what does that mean? And then she just goes, do you want a job? And I'm like, nah, I'm trying to play football right now. Like maybe one day I'll want a job or something. She's like, whenever you want a job, let me know. And she offered me a job to work for like the wildlife or resource. So that of just me just walking around with a flashlight and answer it. It's kind of like chemical question.
This was the year after he had his class.
Yep.
So the potential is there.
So that was pretty funny because she just kept looking at me like, you know this? And I was like, wow. Keep pointing at me.
Doesn't everybody? Every security guard.
I was like, I don't think you know. All right. So, this is my talk, my life after Tiffin. So why did I choose Tiffin? I transferred here to play football. When I transferred into Tiffin, the only thing I knew about Tiffin was that we would beat them in football by 100 points. Like I played for Northern Michigan, and Tiffin was kind of like just like a stat game. So when I decided to leave Northern Michigan, my coaches, they got fired. When I decided to leave Northern Michigan, I was going to go to Grand Valley, which were like the Alabama of D2 at the time, or Eastern Michigan, because they had Adidas gear, and I love Adidas. Somehow, I don't know how, but I get a phone call from Tiffin, and they're like, hey, are you Eric Davis? I'm like, yeah, they remember me from when I played at Northern. Whole bunch of talks happened. Next thing I know, they're like, hey, get a copy of your unofficial transcripts and send them to us. Next thing I know, I was accepted at Tiffin University and came down here and played football. My biggest fears of coming to Tiffin was not being able to, well, some of my biggest fears I guess I had in life was like not being able to take care of my family. I have 7 brothers and sisters. At the time, I only had 3. I just actually discovered 3 more that my dad had other kids, so I have other siblings. But being able to take care of my sister, you know, one of my big things when I was at Tiffin was when you do your internship. I did an internship with a hand therapist or an occupational therapist. My oldest of my sisters, one of my oldest of my sisters, she was born, and when she was born, the umbilical cord was wrapped around her neck. So when she came out, she had developmental issues, and like one thing was when she was younger, the ability to walk. So she had to go to an occupational therapist. So I was like, I'm going to become the number one occupational therapist in the world, and I'm going to have my sister be able to walk and all that. So now she's fine. She's like a normal teenage girl now. But then it was not making it to the NFL. Like, I'm gonna be honest with you, until I met Dr. Shu, like my life goal was to like go play football. Like I never thought. I tell him all the time, when I finally decided to retire from football, I didn't know what I was gonna do in my life. Like, and I remember he called me. I called him. I'm like, Dr. Shu, I don't know what to do. He's like, why don't you join grad school? I'm like, I'm too dumb for that. I can't. What? Like, they're gonna be doing experiments on me. And he goes, when you're ready to be an adult, call me. We'll get you to grad school. I made the choice and I went to grad school. And then moving back home and being stuck. Like, I never wanted to just like move back home. That was a fear of just moving back home and like just getting a regular job. Like, I wanted to do something with my life. My biggest fear of attending TU. One is not getting any playing time. So, you know, transferring to a new university, they already have their people there. And even though they're bringing you in, you know, they might not play you, which is something that kind of happened to me. Living in Ohio. I had never been to Ohio a day in my life. I didn't know anything about Ohio. All I knew about was Ohio State and Ohio State fans. That's all I knew. I didn't even know where Tiffin was. Like, the only time I had my 3 years at Northern, Tiffin had always came to us. So I never traveled down to Tiffin. And well, the year that we did travel to Tiffin, I was redshirted. The other 2 years, they came up to us. So I had never been to Tiffin, didn't know where it was. I knew where Finley was, but didn't know Tiffin was that close to it. And not getting along with people. You know, you're going to a new place, a whole nother state. You don't know how people are. So that kind of scared me a little bit. And then just being out of Michigan, you know, being out of your comfort zone is something really, you know, different. Like now, it doesn't bother me now because like I travel so many places. But back then, it was really something, you know, when you're 20 years old, it's kind of like you worry about that. The biggest challenges in attending TU were being out of Michigan, like I said, being out of my comfort zone, being away from my family, and being in a town where football is not the biggest priority. So when I was at Northern Michigan, if you were a football player, it was like when I was at Northern Michigan, I remember I was dating this girl, and I went to a Twilight New Moon that just came out. And I went to the movie, and the next day we had spring ball practice. And this group of like 40 little girls remembered me from the movie. And I was just signing autographs. I remember the coach was like, why do these little girls know you? And then I thought about the Twilight movie. He was like, who's Twilight?
That's the family.
So, you know, that like coming to Tiffin, it wasn't really that like, when I came here to Tiffin, I think the team had just got, Gary Goff was the coach at the time. He had just got here and he was doing a lot of like, you know, getting the team back. The team was really bad. And I guess he like cut a lot of people and was just trying to get the image of the team back into the right image. So, you know, when I got here, town hated football. Like it wasn't a big, like if you played football, they'd be like, ew. So that was something. Then like the biggest challenges I had was, so I didn't get the playing time that I wanted. That was a real big challenge. And I remember sitting down and talking with I talked to Dr. Shu about everything. Like I was basically like his TA without him having a TA. So, that was something that kind of bothered me. Dealing with the death, my best friend, he had ended up dying over a drug overdose. So that was something I was dealing with while I was here. But, everything turned out to be better than it. So then my first year at TU, the environment, it was very laid back. Like when I got here, like Northern Michigan is in the UP, and it's like the biggest town in the UP. And then being a football player, it was just like everything was open here. Here it was really laid back, like everything was really quiet. You could wake up in the morning, hear birds. You just, everything was really laid back.
Wasn't as cold either.
It wasn't as cold either. It definitely wasn't as cold. And I mean, everybody was super friendly, like being around in the town, because like when we first drove in, I'm like, I had never seen soybean fields. So I seen soybean fields, I'm just like, I'm with my grandfather, and I'm like, what did I get into? Where am I at? I had never seen a drive-in movie theater, like when you drive in, like back in the 40s, like I had never seen that. I was like, oh man, this is gonna be crazy. The facilities, they are not what you have now. Like you just heard us talking about, our lab was a garage. Like I remember, going from Northern Michigan to coming here, we had labs at Northern Michigan. Like one of the elements on the periodic table was discovered at Northern Michigan. I can't remember Earth Rain, one of the atomic ones, and I'm just like, I'm going from that, and then I come here and I'm like, we're in the garage. I think they had just built the dorms over there, those apartment dorms.
Yeah.
The quads had just been built, and Heminger had just been built.
That's right. Yeah, it opened in 2011.
Yep, Heminger had just been built. So, and I remember coming here, and people they were like, hey, don't drink the water at Heminger, or don't drink the water at the apartments, because I guess where Heminger was at, that was like a big garbage. Like you would just go and just throw your garbage over. Yeah, so they were like, hey, don't drink the water there. So I was like, oh,
seriously? That's why we don't drink the water?
Hold on, but I didn't figure that out until I did my internship with the hand therapist, and me and her would travel all around. We'd be in Fostoria and be everywhere. And I'll tell people I was a TU student, they'd be like, oh, don't drink the water. I'm like, y'all keep telling me that, and I don't like it. So they were what they were. Fellow students, I was around football players most of the time. So when I did take classes with the students, it was good. I loved it. I loved it. It was honestly, out of all the universities, if I could choose to go back one, it would definitely be Tiffin. My senior year, the environment still laid back. Facilities, they didn't change. We didn't get anything my senior year. Fellow students, like I said, I was around football players most of the time. So, I always had a good time and everything was always good. My internship, so I did my internship with an occupational therapist named Chris Bowles. She was working at the hospital. I don't know if she's still there or not, but she specialized in hand therapy. So I didn't know there was so much intricacy with the hand. So we would do a lot of hand therapy stuff for outpatient. Then for inpatient, there would be times where we would have to teach people how to put their shoes on, put their socks on, put their clothes on, but we would be in the hospital working with patients. So that was really, really cool. I think I did the internship for the whole summer. It was fun. I literally traveled all around Tiffin, met a whole bunch of people, loved it. What was I gonna do next? Was I gonna leave or was I excited? I was nervous because when I left Tiffin, I was like, okay, I'm about to pursue my football career. I worked real hard. I'm gonna be NFL first pick, all this stuff and that. And I had little problems with the football coaches here, but I still had connections other places. So I just thought I was, 14 NFL career. And it didn't turn out that way. 14-year NFL career didn't turn out that way. So, still a little nervous, but I always had Dr. Shoup in my corner to help me. Looking back at my 2 years at TU, what I'm glad that I did, I'm glad I took Dr. Shoup's chemistry classes, because before I took his chemistry classes, I took chemistry at Northern and I hated chemistry. I was like literally my chemistry teacher at Northern Michigan looked like he was in the movie Revenge of the Nerds. He had pocket protectors, suspenders, the big glasses. I'm like, I don't want to be like this. And then I meet Dr. Shoup, and Dr. Shoup was just I'm like, wow, chemistry teachers can be normal? They be normal people? I'm like, oh, wow, hey. I think I like that. So taking these chemistry classes really motivated me to be where I'm at now. What I wish I did, surround myself with like better people. Like I was around mostly football players, and mostly football players get degrees in like gym. Or like I can't remember the one what it was here, the one all the football players did here, but you know, like you always want to be around people that's gonna like push you academically and like whatever you do. And they didn't. I was the smartest. Like I didn't. Like golf and all them would have me tutor them. What I'm glad that I didn't do, I didn't drink or like live the college football life when I was here. I kind of just focused, did chemistry. Like there'd be times where I would call Dr. Shoup at like 12 o'clock at night and be like, hey, I need help with this organic chemistry problem. So I didn't like live the football player life. So my career path. So where do you work now? I'm a graduate student at Wayne State University Chemistry. So I got accepted in the Wayne State's chemistry program. It's a five-year program. There have been people that have been there for 8. It's paid. If you get into grad school for PhD in chemistry, not masters. I don't even, like we do have, you can master out, but most people, when you get into the chemistry program at Wayne State, you are going for a PhD. They do pay, they pay your insurance, they pay, you got life insurance, like all the adult stuff, they handle all that. And you come in your first year, you have to teach. You teach whatever you're comfortable with, they let you choose organic, inorganic, gen chem. We have something, I can't remember the name of the class, but it's like baby chemistry. So like a chemistry before you get into like actual chemistry, you can teach that. I taught 2 years of gen chem. Job description. So what I do now is, when I started off at Wayne State, I was in a pure mass spectrometry lab. So just a little snippet of what mass spectrometry is. Mass spectrometry is an analytical chemistry method where we discover, analyze, quantify molecules by their molecular weight. So everything has a molecular weight. So if you see here on the periodic table, weights, right? Everything has a weight. Every molecule has a weight, everything has a weight. And I can use what is called a mass spectrometer to see the weight of that element or the molecule that is made up of those elements. So you guys do forensic science. So you know how like when you watch the forensic science shows and the lady gives her husband arsenic. Well, you can use mass spectrometry and see that arsenic in the blood. And that's how, you know, I didn't know that until I got here and Dr. Shoup was talking about it in class one day. He was like, you ever seen CSI or anything like that? He's like, they use chromatography and mass spectrometry. That's how you discover, you know, how the wife killed her husband or something. And, you know, that is technically, yes, it's used for that, but I use it for research of HDACs or histone deacetylases, which are very prevalent in cancer. It's a protein that's overexpressed in cancer. And I use it for kinase proteins. So kinases also are a protein that starts up a chemical process called phosphorylation, which phosphorylation is very prevalent in also cancer cells as well. And I use mass spectrometry to study those proteins, along with other biological tools. How did you obtain this job? Dr. Shoup making me apply. Like I said, I didn't believe that. I was like, hey, I'm not smart enough to do that. Dr. Shoup, what are you talking about, man? And he's like, you're the only football player that ever passed my class. You're smart enough. So
Who took my class?
and took it. So, you know, like I said, I remember him talking to me and I'm like, man, I can't do that. They're gonna be doing experiments on me. Like I've played football since I was 5, probably got I took a psychology class and I remember one of the teachers, I was telling her about it. She was like, you probably have CTE. And I was like, wow. All right. So, you know, I just never thought that I could be at this level where I would be doing this or doing chemistry until Dr. Shoup. So,
and you made a decision your senior year with your football team, correct?
mm-hmm. So my senior year here at Tiffin, like it wasn't going the way I wanted it to go. So I kind of was like, all right, like, what am I going to do here? Like, this isn't going the way I wanted to go. I'm not getting along with the coaches. Something isn't right here. So I was like, hey, I need to focus on this academic stuff and then put the football to the side. So, you know,
that was a challenge because you've been doing it for a long time.
Mm-hmm.
And how do you, as you heard before from other speakers, how do you handle that? And your senior year, you had instrumental, biochem, and but for the hard courses, and you're dealing with all the labs with this kind of stuff, plus practice.
Yeah.
You know, and so you got to make a decision. And that was a tough decision to make, but it was the right one.
And I mean, and I was taking these classes, so like I wouldn't even leave that lab. So it'll be like Gen Chem, Dr. Shoop at 8. Everybody leave, I'm still sitting there, organic. Hour break, come back to the lab, instrumental analysis. Take a 2-hour break, come back, instrument analysis lab. Practice. So I literally stayed with Dr. Shoop my 2 years. Every semester I was with him for at least 4 to 6 hours a day. So my career. So my career, I have excited cases and projects. Had a TM with education, what certain professors made us do. I was glad they made us do it, and my future career path is becoming Dr. Davis at the end of this year. So just to talk about my research, this is these are some slides from my 4th year talk. So at Wayne State, when you get into the grad program, what they do is you're not like in the like if they accept you, you're technically not in the program, you're a candidate. So the first thing you have to do is you have your first year where you have to teach. So usually with most people, when they're teaching, they don't have your first semester, you don't have a PI yet. So you're just teaching, you're getting used to teaching, and you also have to take classes your first and second semester, so your first year. So you're teaching, you're taking classes, and you're rotating through different labs, because there's 5 disciplines of chemistry. There's physical chemistry, there's organic, inorganic, analytical, and biochem. So you usually go towards, like, when you first get there, they give you this test, and it's the 5 disciplines of chemistry. And whatever you do good on, that's usually what, like, the lab you try to, go to. So I did good on organic, analytical, and biochem. I'm horrible at inorganic. And physical chemistry is like quantum chemistry and like basically like all like the math part. I didn't want nothing to do with that. So
you're not alone with that, by the way.
like I remember I had to take quantum chemistry, and I called Dr. Shoop, like, hey, Dr. Shoop, I need help. Can you help me with this quantum chemistry? He goes, what is that? And I'm like, it's this, like, it's just all linear algebra and matrix algebra, but we had to do it all by hand. The professor made us do it by hand. He's like, if you can do it by hand, you can do it on a computer. So your first semester, you're teaching, you're taking classes, and you're rotating through people's labs. So I already knew what lab I was gonna go to. I was gonna go to a lady named Dr. Sarah Trippin. She did pure mass spectrometry. That's all I wanted to do was mass spec. She had 3 mass specs in her room. And what she did was, so on mass spec, there's multiple parts, but the main parts are front end and back end. She worked on front end, so ionization. One thing about mass spectrometry is you can't analyze anything if you can't ionize. Ionizing, it means taking it into a gas phase. So like I said, like if you have this person's blood, right, and the lady poisoned them, we have to be able to get that blood and everything into the gas phase and get everything that's in the blood into the gas phase, so then we can then measure blast molecular. So that's what she worked on. So she had discovered a revolutionary way to get analytes into the gas phase by ionizing them without using any type of outside energy source, which sounds crazy. How do you get a liquid or a solid into a gas without any energy added, like heat or electricity or a laser or anything like that? So I worked with her for 3 years. And then after I worked with her for 3 years, COVID hit. And then when COVID hit, all the instruments in the lab broke down. We couldn't go into the lab, so I needed to find a new lab. So I joined the lab with a lady named Dr. Flum. Dr. Flum is a pure biochemist. I don't know anything about biochemistry. I went analytical chemistry and I do mass spectrometry. She loved me though, because she always wanted to do analytical chemistry. She didn't know anything about analytical chemistry, and especially mass spectrometry. So I was kind of like, a diamond sitting out there that she could grab. So I joined her lab, and in her lab, we combined mass spectrometry with chemical biology to study human elements. So the projects so in this lab, there's 2 projects. There's the kinase project and there's the oh, it doesn't show up on the screen. So there's a kinase project, and there's a histone project. So normally in that lab, we focus on cancer. When I came there, I didn't want to research cancer. Everybody researches cancer. So I wanted to apply kinases and histone deacetylases to other projects. And she was like, hey, if you want to do it, okay, let's do it. So I researched using her biological tool. I researched kinase with this involvement in chloroquine-resistant transporter proteins of the human malaria parasite. So in a nutshell, what that means is that there is and I'll get into it, a chloroquine-resistant transporter protein in human malaria. So basically, you use chloroquines when treating malaria. The malaria parasite is becoming resistant to it. And what we know is that kinases, which I'll talk to what kinases are for this talk, kinases are involved with this resistance. Then my second project, now usually in the lab, you do one or the other. She decided to give me both. So not only do I do kinase, I do the histone deacetylase or HDAC proteins and their correlation with sickle cell anemia. So just to give you a little, we're getting to that talk as well, but histone deacetylases are proteins, and these proteins are being overexpressed in sickle cell. But here's the thing, they have been using something called HDAC inhibitors. And HDAC inhibitors have been shown to work, but here's the thing, they don't know how they work or why they work. They just know that if someone is going through some kind of sickle cell crisis, if they give them this HDAC inhibitor, the crisis stops. But they don't know the molecular mechanism that it takes to be able to get to that point. And that's where I come in. Hopefully I can figure that out. So we're gonna start with my first project, which is kinase involvement with chloroquine-resistant transporter proteins of the human malaria parasite. We start off, so let's start off with kinases. Why should we study protein kinases? That's because they are involved in something called cell signaling. So right now, your body is doing cell signaling. Right now, like if you're hot or if you're cold, that's your body going, hey, do this. Hey, this is too hot here. Send in a signal somewhere else. Hey, we need to fix this, regulates body temperature. So it's constantly sending messages back and forth. Now, how it normally works, oh, I wish the laser pointer could point at that. Why won't it show up on the screen? Okay, so you have a signaling molecule. That signaling molecule, it relies to a receptor on the outside of cell membrane. It then activates that protein. It then sends a transduction signal down into the cell, which then activates a cellular response. This is an example of this. This is the EGFR, kind of like it's basically showing how EGFR, which is epithelial growth receptor hormone, how it works in the body. So what happens is when that EGFR right there is the protein, and when a receptor molecule lands in there, as you can see, it lands in there, it starts to phosphorylate. So that P, all those P's stand for phosphorylation, and that's what kinases do, they phosphorylate. So everything you see with a P has a phosphorylation, has a kinase that's phosphorylated. So that can, those P's, as you can see, can lead to a bunch of different things. So you can see it leads to cell survival, cell proliferation, cell survival, cell migration, all those things. Now, the reason why that's important is because let's say something doesn't get phosphorylated or something gets over-phosphorylated, right? If it gets over-phosphorylated with the cell proliferation or cell survival, the cell won't die. So if the cell won't die, what happens? Or if the cell keeps multiplying, what happens? You get cancer in the cell because the cell won't shut off. Or if the cell, or if something doesn't shut off, then you could get cancer. There's a lot of ways to get cancer, but like with phosphorylation, either something doesn't turn on or something doesn't turn off and you get cancer. So we need to be able to study this. So how science has decided to study it is with something called a gamma phosphate modified ATP analog for kinase catalyzed cross-linking. That's a lot, but we're gonna get into what that means. So what happens is you have your protein substrate. Your kinases, what it does is it will take this last group of ATP or adenosine triphosphate, and what it will do is it'll come in and it will take this last phosphate group and put it on that group right there, that alcohol group. That's how the kinase transfers the gamma ATP on there. So what we have decided to do was we have decided to modify this last group here with an R, and we do that.
I'll get your point back and keep going.
Okay, yeah, because I don't know why it won't. It's hard. So
because of the screen, it's on the projector.
Okay.
Yeah.
So then what happens is, so what we decided to do was we decided to modify that ATP, and we call it an analog. So what we do is we put this arylazide group on there. So when we put this group on there, what it does is this group is light sensitive. So what happens is the protein kinase will come and it will label the protein that we want. So you see it took the gamma modified ATP, the kinase came in with the kinase protein and then put that last group that we modified onto the labeled phosphoprotein. So that's what we want to do. So then what happens is we introduce UV light in that arylazide. What it does is it'll then act like a fishnet and it'll capture whatever is around this protein. It'll capture associated proteins and it'll capture the actual kinase that's doing the actual labeling of putting that gamma phosphate group onto that protein. Now that's cross-linking. So in our lab, we decided to add an extra step to it. So what I just explained to you was the kinase catalyzed cross-linking. It was kinase catalyzed cross-linking, but then we added something called a streptavidin purification. So what happens is you have your kinase, you have the protein that's associated with, you have another protein. You have that gamma modified phosphate group. You have your photo cross-linker here, which was the ATP arylazide. You have the kinase doing its thing, attaching it to the associated protein, but we have put onto that gamma modified phosphate group, we have something called a biotin tag. Now remember the biotin tag, because the biotin tag is going to be really important for the streptavidin purification. So once UV light hits it, everything binds together now. So all this stuff is attached together like a net. Here's where the biotin comes in at, this biotin tag peptide. We use something called streptavidin. Streptavidin and biotin have the highest affinity for binding for each other in nature. So we use a streptavidin bead to then enrich all of this stuff out of solution because we do it in a lysate. And in a lysate, there's a bunch of cells, but we only care about the kinase that we want to grab off. So we do a streptavidin enrichment, where we then, anything that is connected to this biotin, this peptide, will then be put out of solution. Then we will then take it to mass spec analysis so we can know what protein we are looking at and what proteins are associated and what kinases we are looking at. So like I said, I keep saying associated proteins. So what can happen is, because this kinase process is fast. So if you ever look at any enzyme, it's just going and it's just putting on phosphate groups. So because it moves so fast, when the light hits it, when the light hits the photo crosslinker, the kinase might have already went away. So then what can happen is we shine the UV light and that photo crosslinker could then attach to a protein that's next to the kinase. So now we can do the same steps, streptavidin purified out, do the biotinylated peptide, mass spec analysis. Now we can see associated proteins that are around that kinase.
Now, again, you're looking at proteins on the mass spec?
Yep.
Which weigh like 25,000 AMUs, right?
Yeah, or heavier.
Okay, we're used to this. We're used to in this lab, weights of about 50 to 60. I don't think you know any proteins in mass spec, do we? I don't think we ever done a protein in mass spec.
Lots of it. So
we're looking at analyzing proteins. They're huge complex molecules. Really complex. So mass spec has to be able to handle it.
What mass spec do you guys have?
We got a variant 22.
Single quad?
Yeah.
Yeah, you couldn't look at proteins on a single quad. And what type of ionization is on front of it? What are you guys doing?
Hot filament, maybe? I don't know.
Okay, so like, is it like EI? Is it chemical?
It's not EI.
it has an element.
I don't know, Dr. Sable's not here today.
Okay. So I mean, so
Remember, we didn't have one in class.
yeah, okay, so usually, okay, so when you're looking at proteins or you're doing proteomics mass spectrometry, you need so usually when you do mass spec, you add a proton to your analyte and then it goes. So when you're doing proteomics, because the proteins are so big, you need multiply charged ions. And I don't have any spectra to show of multiply charged ions, but usually when you do proteomics, you need a high mass resolution instrument. So you need something that, if you ever hear anybody say MALDI or MALDI-TOF, that's usually a high mass resolution instrument for proteins. Or if you hear somebody say Orbitrap or anything like that, that's like proteomics.
Just so you know, he's talking about TOF, that's time of flight detector. Trap is ion trap detector, they trap it. We have a quadrupole. And all a quadrupole does is that it deflects it at different weights, it deflects it in different locations. So you have quadrupoles, ion traps, and you have time of flights. How long does it take to go from A to B? The bigger ones take longer time than the smaller ones. That's what I mean by that. But these are all parts of a more complex system.
I could spend like 5 hours talking about the different mass spectrometers. Like I love that stuff. So yeah, so we use a high mass resolution, which I'll get more into that into the talk where I show about it. So K-class, we capture the proteins that are involved with kinases. We want to see what kinase, we want to see what proteins we're going to see. Now let's apply it to something. So we applied the K-class method to Plasmodium falciparum, aka malaria parasite. So the malaria parasite is becoming resistant to chloroquine. Chloroquine is a small molecule that is used to treat malaria. How chloroquine works is that you take it, the parasite eats it. Inside the parasite's gut, right? It has a mechanism where, because, let me go back a little bit. Malaria, how it works is it eats blood. So your blood is split into two, it's hema and globin. The heme is actually poisonous. What the malaria parasite can do is that it can eject the heme out of its body so it doesn't die. So what the chloroquine does is that it stops the malaria parasite from being able to eject that heme. The heme then builds up, kills the parasite. The parasite is becoming resistant. So working with Dr. Lanzer from Heidelberg University, I think in Germany, I think?
Yes.
Yeah, Heidelberg in Germany. Yeah, there was plenty of times where, because their time zones are different, where I had to be up at like 2 in the morning to have meetings with this guy and people in his lab. We decided they know, this is kind of what the parasite, so basically they know the phosphorylation sites. So they know with this chloroquine resistant falciparum, they know where it's being phosphorylated at. And it's being phosphorylated at the serine 33. So when you see something like this, that means the peptide. So proteins are made up of peptides. So they know serine 33, threonine 416. And when you see the number, that's just the number of where it's at in the protein. So proteins can be made up over, it could be thousands of peptides, it could be 4 peptides. But no, I mean amino acids. That's what they do. So they know here, here, and here, that's where phosphorylation happens. So since they know that, they want to know what kinase is phosphorylating these sites. And that's where I came in at with applying K-class. So what they have to do is with K-class, the most important part with K-class is that we have to have this bioaccumulated peptide. So with that, we had to get these peptides created. I don't know how people create peptides. I never want to do it. We just buy it. So this is the peptide, what I like to call a wild type. This is the actual peptide with the amino acid that is being phosphorylated, the serine. So as a control, when we do this experiment, we want to see what's being phosphorylated, but we also want to compare if that's actually being phosphorylated. So we have a control where we switch this serine to an arginine. Like I said, I don't know how they do this. They do it at a company. I don't ever want to do that type of synthesis. That's more synthesis chemistry. I don't like it. It's like cooking. And I'm bad at cooking, so don't like synthesis. And then we have to put a biotin on there because, like I said, we're trying to get this peptide with the biotin. That was for the Serine 33. Then for the Serine 411 and 416, we basically did the exact same thing, except we just, so if this is the wild type, we would replace one of the amino acids from the wild type with an alanine, and then we just basically just made a bunch of negative controls. And you'll see why these controls are important when we get to the mass spec part. So how it starts off with is we start off with the DD2 or the lysate. So this is the Plasmodium falciparum lysate. A lysate is they just take, do you guys know what lysates are? Basically, they took the parasite or whatever and they lysed it. So they made everything inside the parasite, all the cells, all everything come out of it. And that's usually done with chemicals. Some people do it mechanically. I don't know how they did theirs. They just sent me the license. So what these are, this is basically my experiment. So my sample 1 is just the lysate and no UV. So remember, UV is used for the crosslinker. If we don't have no UV with the crosslinker, it won't crosslink. It'll just be floating around the solution. And that's a negative control. Then we have another negative control where we have lysate, we have the wild type peptide. So without the peptide in the photo crosslinker, which is the ATP-rLazide, and no UV, we should technically get no cross-linking at all as well. We shouldn't be able to see anything. Then this is the actual experiment where I have the lysate, the peptide with the biotin tag that I just showed, UV and ATP-rLazide. So that means when we run a gel, which you'll see, we should see a lot of staining because we track things and now we're trying to look at them. And then we have a mutant, then we have our mutant here, which with our mutant, we should technically see no cross-linking or just very little cross-linking because it's a mutant and there shouldn't be any kinase phosphorylating anything because it can't because there's no serine because we changed it to an arginine. So what happens is I have those, I mix those all together in Eppendorf tubes, then I incubate them at 31 degrees Celsius for 2 hours. The reason why we do this is because we have two reactions going on within these tubes. We have the reaction between the kinase and the, what we like to call protein substrate, and that takes 2 hours. That's the biological interaction. The other interaction is the UV with the ATP-rLazide or the photo crosslinker. That takes nanoseconds. You guys weren't there for my 4th year talk. They give you questions at the end. And at the end, one of the professors, Dr. Shoup was there, one of the professors goes, why does it take 2 hours? And I'm like, and I just sat there and I had to think about it. I'm like, I said something. And I just remember at the end, my PI comes up to me. She's like, the way you answer that question was this, because there's 2 reactions going on. So now I know why we do it for 2 hours.
For defense.
Yeah, this is for defense. And then, so we use UV to, I'll get to that first. So we have a streptavidin enrichment where, like I said, we're going to take that biotin tag that's on everything. We're going to pull it out of solution. And then we're going to do an SDS page followed by a CY5 streptavidin stain. So what the streptavidin stain is like I said, we have our photo cross-linked everything together. We have this biotin. We have this CY5 with streptavidin. They are going to create a covalent bond together. And when they're stuck together, we can then put a developer on there and then bring it to an instrument that's called an imager. Then we'll be able to see what we've captured in the gel. So what that looks like is this. So if you see one is here, which we shouldn't see anything. There's no peptide, there's no UV, there's no nothing. Then we have our peptide, UV, and our crosslinker, and it's very light. Then we have the actual experiment here with the peptide, UV, and the wild type. And then we have our number 4, which is the mutant. Now, it didn't turn out how we wanted it to be, because in a perfect world, this would be the dark lane, and these 2 lanes would be very light. The reason why this happened is because this UV crosslinker is very sensitive to light. So once light hits it, it's going to start crosslinking. So what possibly could have happened was I wasn't moving fast enough with this sample and light started hitting the crosslinker, and the crosslinker started crosslinking with everything. Now, what was funny, because Dr. Shoup was there, was one of my people, he's actually in my committee, so I don't know why he was doing this to me. But he was like, you know, we use UV light. UV light, as you know, you're not supposed to have it on your skin or anything like that because it causes cancer. He goes, so you telling me that the lights can give you cancer? And I just look at him and I go, and before I could answer, two other professors kind of like answered the question for me before I could even answer. So it was funny though. Like he hit me with that, and I remember looking at Dr. Shoup like, this is what I gotta go through.
I was sitting right about here.
Yep. He was sitting about that far away from me, and that professor was right here, just looking me dead in the face and said that. So after we do the SDS page, which have you guys ever seen a gel being ran? So basically what a gel does is SDS page is basically you have your proteins and it separates proteins by the molecular weight within a gel. So the heavier you are, you're at the top, and then you move down, and those are the more smaller proteins, and they separate them, then we visualize them this way. So after doing all of this, which I don't like doing any of this, I don't, but I had to learn it. All of that stuff that I just talked about, I hate doing, but I have to do. Now we get into the fun part, which is the LC-MS or mass spec analysis. What I use is, when it comes to proteomics, there are two types of analysis. There is bottom up and top down. I focus on bottom up proteomics, or AKA shotgun proteomics. What happens is you get your biological sample, you can get it from anywhere. You then extract the proteins from that said sample. You then digest those proteins into peptides. So when you do proteomics, the technology hasn't got to the point where we can do whole proteins yet, because proteins are huge. So we got to chop them up into little pieces and then put those little pieces back together like a puzzle to discover what protein it is. Then we bring it to the LC-MS. LC-MS stands for, so I don't know if you guys have used it, but I know you guys do have a liquid chromatography instrument, right? So because we chop that protein up and there's so many proteins in these samples, we have to also separate the peptides. So we separate the peptides, and I could get into separation for like 3 hours too, but we separate the peptides through the LC, then they go through the MS, mass spec. So basically, we're analyzing them, and they're going through two mass spectrometers in one for us to be able to analyze them and then discover what they are. After we do that, we process them with something called bioinformatics. So if you guys have heard anything about mass spec, you get a spectrum. What happens is once we get that spectrum, we plug it into, I personally use PD, which is Proteome Discoverer. We plug the spectra into this platform, and in this platform, what it'll do is it'll take those spectra and it'll match those spectra to a database. And in that database, it'll put the spectra together and be like, hey, it's this protein. And that's how we discover proteins that are in lysates. And that's how we discover them. So we quantify them and we qualify them all at the same time. Because we also get a quantification of proteins, and that quantification is in ion abundance, which ion abundance is how much of it is there. So the first part starts with the sample preparation of what I just said. This is the sample prep. This is also what we call wet chemistry. I don't like doing it. I can't wait till I get to a point where I just get the samples and do the mass spec. Sample preparation of gel. So once we do that, right, we have to run it through a gel. We have to do something called an in-gel digestion, because we have to get the proteins out of the gel. So what we do is, like I said, I have my samples, ran my samples into the gel. The reason why we do this into the gel is because a lot of these samples have biological buffers. Biological buffers have a lot of salt in them. You can't put salt in a mass spec. It'll mess up the mass spec. So we have to desalt it, and we desalt it by running it 1 meter into the gel. Then we cut it out of the gel. We cut the gel into pieces. The reason why we do that is because we didn't want to dehydrate the gel pieces so that we can then do an in-gel digestion with trypsin. Once we do the in-gel digestion, because remember we have the whole proteins in there, we want to chop them up using trypsin, using the in-gel digestion. Then we collect those peptides, and I bring them over to Wayne State Medical School to my co-PI, Dr. Stemmer, who runs the mass spec core or proteomics core at Wayne State University. He's a pharmacist by trade, but he learned how to use mass spec because he's like, it's one of the best analytical techniques. So he got one of the best instruments in the Midwest, which his instrument is amazing. Like it looks like Knight Rider, like the car Knight Rider. That's exactly what the instrument looks like. I'll actually show a picture of it. So he's a PI of the proteomics core. And he's been teaching me proteomics mass spectrometry because there's multiple types of mass spectrometry. You have proteomics, you have lipiomics, you have metabolomics, you have regular mass spectrometry where you're just looking at single molecules. And each one takes a different set of skills. And I first learned just regular mass spectrometry front end. And now he's teaching me proteomics mass spectrometry and back end, which is the bioinformatics and all that. So first part we start off with is this is my LC instrument right here, the Vanquish Flex HPLC system. The column, so usually I don't know how you guys LC system is, but usually you see a column and it's like this long kind of silver tube. Is that the kind of one that you guys have? So you guys have the long silver tube. This one, the column is here. So the column, in proteomics, we directly spray from the column. So you don't get any kind of like dead loss. And it's just easier than kind of like a preparatory column because we're also working with very small amounts. Like we're only injecting like 2-3 microliters onto this column. So we don't need a real long, big column because we're not working with like milliliter volumes. And we sprayed this column can be heated up. Heating helps with being able to ionize proteins because proteins like to aggregate together. We don't want that. Clogs my column. This column, just this piece right here, $2,000. I have 7 of them. I've already blew 3. So you got to be careful with those. So that's the instrument. The instrument can hold up to like 200 samples. So I can really just load it up and just spin it around and choose what samples I want. So once we go through the separation, we get into the instrument. This is the instrument. See, like this light, so it looks like Knight Rider. This is the instrument.
It's a great TV show with a 1989 Firebird, starring David Hasselhoff.
Yep, the dude from Baywatch, like
exactly.
Old school Baywatch. Yeah. So this is the Orbitrap Eclipse. This is the latest model instrument. So he has literally the best instrument in the Midwest. Ohio State with Vicky Wysocki, she has a mass spec core. And she's like up there in the mass spec community. Like if she says something, like everybody does it. She doesn't even have this instrument. So it's like I get to work with this instrument. And what's funny is how much do you think mass specs cost? This is about a $2 million instrument. Oh yeah, about 2 just for that. And this isn't the base model. So he had extra attachment added onto it. So I think it's about $2.5 million instrument. Yeah, scaring me at first. So yeah. So most mass specs are like, I mean, how much did you guys pay for yours? Like
$25,000.
$25 for a single quad. Yeah, this is in Orbitrap. So it's an Orbitrap, and it has like a ion mobility attachment, so you get more separation. So you can go LC separation, ion mobility separation, then straight to the Orbitrap, which is high mass resolution. So and then this is so remember when Dr. Shuk was talking about how I took the instrumental analysis class? Mm-hmm. So we didn't have instruments. So he would put schematics up like this, and then we would have to fill in the blanks to what everything was. And that's how we learned instrumental analysis. So they weren't $2.5 million ones either. Yeah. Simple. So here's just like so I could get into all day about what all this stuff means. Just know that it gets analyzed here with the ultra high field Orbitrap mass analyzer. This is where we're identifying all those peptides that the proteins into the peptides that we chopped up. This is where they're being analyzed. So after that, we then take that spectra, we put it into the bioinformatics. This is my computer. I think this computer, my PI, she had a lot of grant money, a lot of funding. She got me my own personalized computer, dual screens. I think it's like 16 core processor. You need a lot of processing power because these databases are huge, and just mass spec data is just like, I have maybe like, you can't see them, but I have like 17 or 18 terabyte hard drives that I just put mass spec data on. They're like, this is Proteome Discover. How much do you think this program costs? 25,000. Just for the program, yeah. So mass spectrometry can be expensive, but the cost pays. So what happens is, now we discovered, when I did the proteomics, this is for the series A. When I did the proteomics, I discovered 1,444 proteins within that sample. Now, we're gonna get into why I had the bead or tube 1 with no UV and no lysate, no UV and no peptide, no ATP, no ATP-rLazide. And we're gonna get into why I had all these different controls. So the reason why we get into these controls is now we do something called Excel math, because we want to look at the proteins that we enriched or pulled out, proteins that are associated with the kinase. So how we do that is we have a bead control and we have a wild type and mutant control, because we want to get rid of proteins that aren't associated. So we want to see all the proteins that was trapped here. So if we see a protein that's trapped here and a protein that's trapped in here, that's bad, because there should be no proteins trapped in here that are associated with this one, because technically they're two different things. And if we see a protein in here, right, that was trapped, and we see that same protein in here, how could that be possible? Because we don't have the ATP-rLazide, nor does it have any UV. So we have to eliminate all those proteins that aren't associated with what we want to see. And that's where we do this with the Excel math, where we do an enrichment. We have a bead over wild, which is in control. We have our wild type over mutant, which is what we want to see. We set the intensity ratio to be greater than 1 or less than 1. So basically what we do is we do some Excel math, // math, and then a number comes up. And if that number is less than or greater than 1, we keep it. That's how we get rid of it. And that's how that works. It's literally that simple. It's really fast. Then we do, this is the one we care about right here, which is the proteins that we want to keep. If it's anything greater than 1.5, so if that protein has a number greater than 1.5, that's what we keep, and we know that's a protein that we enriched. So anything less, we get rid of it. Anything higher, we keep. Once we do that, I then made a hit list. Also doing that, we made a hit list. So out of that 1,441 proteins, only 98 proteins made my hit list. Out of that 98, 4 were kinases. So due to the protein that does the phosphorylation, 94 were non-kinase proteins. So everything in blue is a kinase protein. And what that means is, in purple, what that means is that we think that these kinases could be the direct kinases that are phosphorylating the Plasmodium falciparum and making it basically chloroquine resistant. Now, to test that, I don't have to do that. I just had to tell them, hey, these proteins are, these kinase are the ones that are doing it. That's y'all job. Now, y'all figure out which one it is. And they do that. I don't know how they do that. There's multiple ways to skin a cat. I don't know how they do it in Germany and their lab. So I did the same thing with the Series B. This is just the, for us to be able to visualize it. Took it to LCMS, did the same process, discovered 1,245 proteins. Out of that, 257 proteins were hits, were enriched, 5 were kinases, 252 were non-kinase proteins. This is not all of them. I couldn't fit all of them on the screen. So, you know, ones in purple are proteins, are kinases that we think are doing the phosphorylating. They'll figure that out. So the conclusion to this project was I applied K-class to the Plasmodium falciparum strain. I discovered 4 potential proteins, 4 potential kinases for the phosphosite of serine 33. I discovered 5 potential kinases for the phosphosites serine 411 and threonine 416. My future direction was to do 2 more experiments with both. I actually did. I got crossover to those proteins, so just biological replicates. So all those proteins in purple that I showed you, they can go through and test whichever ones they want to see if those are the exact kinases doing the work. And actually, because they liked my work so well, they had a couple more projects that they want me to help with. So they threw that on me. So helping them with some other projects now. Now we're on to my second and last project, and this project is very important to me because this is me applying our HDAC trapping method, which I'll talk about that, to sickle cell anemia. I don't have sickle cell anemia, but I'm a carrier of sickle cell anemia. So I kind of look at it like kind of like being a mutant. Like, cause like, I don't have sickle cell anemia, but because I'm a carrier, I have kind of like an immunity to malaria. Which here's the thing right here. Those projects, that happened by coincidence that they overlap with each other. Like when I got handed these projects, I didn't know that they were gonna overlap with each other. So me and my PI, we laugh about that. And it's like, hey, you know, malaria's involved with sickle cell and all that. It's like, oh, so that was pretty cool. So let's get into, so epigenetic regulation, gene expression by histone acetylation and decetylation. So that's a lot. So we have histone deacetylation, or HDAC. Okay, why is that not showing up? All right, I don't know why that's doing that, but so basically what happens is, what it does is acetylation. So what it'll do is, what a hat will do is that it will, so HDAC takes off the acetyl group. So this is the acetyl group. When it becomes an HDAC, it takes it off and it makes it a positive charge. If it's HAT, or histone acetylation transferase, it'll put the acetylase group on and make it neutral. The reason why it does that is because in DNA, it's these things called histone proteins. In these histone proteins, they have lysine-rich tails. These tails are positively charged. DNA has a negatively charged backbone. So what happens when you have a positive charge and a negative charge? They come together. So when they come together, they close off the DNA for it to be transcribed. So nothing can happen. You can't transcribe the DNA, can't make proteins, can't do whatever. So when histone deacetylase happens, it comes and it takes that acetylase groups off, makes it neutral. Now you have kind of a negative charge backbone and a neutral charge lysine, and they pull each other apart. And what happens when they pull each other apart? Well, when they pull each other apart, they become open for transcription. So that's HAT. And I don't know why it's doing this, but you get transcription. Transcription is stopped when it's closed. And when it's open, transcription has the ability to be activated. So histone deacetylase stops transcription. Histone acetylase transferase makes transcription happen. So what happens is with these HDAC proteins, there's different isomers. So you have a bunch of different HDACs. You have HDACs 1 through 11. We study the HDACs in class 1, 2A, 2B, and 4. We do not study 3. The reason why we don't study 3 is because for the activity of the class 3 HDACs, they use NAD+, while the other HDACs use metal. What that means is, in order for them to do their job of deacetylating and acetylating, there needs to be some type of metal ion present. The reason why we study the metal ion present is because they are all pan-inhibited by this molecule called SAHA. And we just use SAHA because it's the easiest. And like I said, it inhibits all of them. So, yep.
Are the metals the same for the different classes?
So they can change. So at first we used to say it was iron. But then we've seen other enzymatic activity where there's been a sodium, where there's been all different types of metals, depending on the class. Some classes use different metals, some classes use one metal. We got people in our lab that study that. I don't. Okay. So yeah, we got people in our lab that can literally sit up there and go through just which metals are being used and all that. I don't do biochemistry. I'll leave that to the biochemists. I specifically study HDAC1 because it's the most studied and for its involvement with sickle cell anemia. So what is sickle cell anemia? Sickle cell anemia is caused by a genetic mutation in the hemoglobin gene. It's a single amino acid subtraction. So you have your normal DNA here, right? What happens with sickle cell, you get, so it's AT, but then it switches to TA. Then when it goes to RNA, you then, instead of getting a glutamic acid, you get a valine. And then what happens is normal protein is created. When it's not changed, when it's mutated, you don't get a normal protein. And what happens is when you don't get that normal protein, you get the sickling of the blood or of the hemoglobin. which when you get that sickling, what happens is, you see you have normal hemoglobin, it's flowing through your blood, it's flowing through your bloodstream, fits perfectly through, it's also malleable. So like the blood cells, like if I could take one out of your body, I can squish it. And it can move and it can fit through the arteries, fit through capillaries. It also holds an oxygen. But when you have sickle cell, what makes it bad is that not only does it sickle, so it can't hold the oxygen, but it's also very rigid. And the worst part about sickle cell anemia is that they tend to aggregate together. When they aggregate together, the sickled blood cells, they start blocking off arteries. So now you're not getting oxygenated blood to arteries, causes pain, death, whole bunch of stuff no one wants to deal with. And it hurts really bad. I've actually got to meet a couple people with actual sickle cell anemia. I'll talk about it later on because it's a really good thing, but I actually get blood samples from sickle cell patients. So histone deacetylation and its correlation with sickle cell anemia. So remember I was talking about those histone proteins and sickle cell anemia. So how do those two things correlate? So what has been read in papers, and just to give it to you in a nutshell, in a simple way to digest, they're using HDAC1 inhibitors for sickle cell anemia. They know that as soon as you take that HDAC1 inhibitor, what happens is you get more production of HbF or fetal hemoglobin instead of sickle cell hemoglobin. Now, when you increase the fetal hemoglobin, your blood goes through stages. So there's it when it's like a CD34 plus or like a stem cell, and in your bone, it grows up into your blood cell. But before that, it's something called erythroblast. So what was basically going on is that you take this inhibitor, and this inhibitor is basically making your body produce more baby red blood cells than adult sickle cell red blood cells, which basically dilutes the sickle cell blood cells out and increases more of the baby red blood cells. Now, they know that it does that, but they don't know the mechanism on how it works. Something else that they know is that at the speed at which it's working, it's more of an epigenetic thing than a genetic thing, but they don't know why. And why that's important is because the HDAC inhibitor is affecting more than just HDAC. It's also affecting other proteins that are around it. They don't know the other proteins that are around it. So that's where I come in. So that's where we have this technique called HDAC1 or histone deacetylation 1, substrate profiling using proteomic-based strategy tracking. This is a lady that was in my lab, Dr. Danusha. When I got to the lab, she had already graduated, but she basically discovered this way of us being able to study HDAC proteins. So how does this work? So HDAC proteins are enzymes. So what it does is that WT stands for wild type. What happens is the HDAC protein comes in, it deacetylates its substrate, then it releases it. So it comes in, Pac-Man monster, eats it, lets it go. Battery popped out. Yep. So then what we do is the battery popped out. So then what we decided to do was we decided to make a mutant. So with this mutant, we made an inactive mutant. So with this mutant, what it does is it'll capture the substrate, so it'll come in with the Pac-Man mouth. But instead of releasing it, the substrate is trapped in there. So now it won't let it go. And then what we'll do is we'll use immunoprecipitation, and we will immunoprecipitate this HDAC protein out, which is we put a flag tag on it. So we will then IP the flag tag out, and we'll be able to discover the protein. But what we want to do is that with this protein, we want to know that it's an actual active site substrate. So what we do is we run another experiment where the mutant has competition with an inhibitor. So that's SAHA. And what it'll do is that if it's an actual substrate, an active site substrate of the mutant HDAC, the SAHA will then bind in there and we won't get this protein, or we'll get less of it. So then what we do is we'll IP all of that out, and then we'll image it and take the mass spec. What is IP? IP is kind of like is immunoprecipitation. So you guys know about antibodies and how antibodies tend to. It's that same principle, so instead of doing it inside of the body, we do it in a lysate. So you have your monoclonal flag tag bead. It's a bead with an antibody on it. This antibody is only going to see the flag tag mutant or the flag tag wild type HDAC. So what happens is, you see that in the lysate, we got our flag tag and we got our the wild type, and it's stably bonded to the substrate. It interacts with the bead. The bead is only going to interact with those two. We then wash, pull them out, and now that's what's left on the bead. Then we do a cypro-ruby stain. Once again, we have these three. We separate them out, and then this is what, in a perfect world, what the gel would look like. So in our wild type, we're going to get proteins, right? But because this process is transient and happens so fast, we're not going to see everything. We're not going to see everything it grabs. With our mutant that's not going to release the protein, we're going to see a bunch of proteins because it's not letting go of anything. Then when we get to our competitor, we're going to see proteins, but we're not going to see as many proteins in our mutant because it has the competition. So this is what we want to see. Then what we do is we see the proteins, we look for the proteins, well, we look on the gel for the proteins that aren't involved in the wild type and not involved in the mutant with a competition. So these proteins here tell us that, oh, we captured something here. We want to see that. We cut those bands out. We then take it to LC-MS analysis. Now, I'm doing this process right now with sickle cell. But here's where the amazing part of this project comes from, and I'm thankful to have this. This lady, you can't see her face because of that, but Dr. Janelle White from the pharmacology program at Wayne State University, she works with direct patients, with direct sickle cell patients, and most of them are children. So Wayne State has a children's hospital where they specifically focus on children with sickle cell anemia. So I actually get to like see the, well, I haven't seen any patients yet, but she gets to see the patients, talks to them, she collects their blood. When she collects their blood, she brings it to her lab. So I'm handling, remember, I'm a mass spectrometrist. I'm handling real live blood samples from sickle cell anemia patients. So I'm getting primary cell lines. Most of the times when you see experiments, they're using cell lines that they bought from somewhere, that someone else harvested, did everything. We know this cell line works. I'm getting a cell line directly from a human being, which is, you don't get that. And I'm getting it for free. I just have to come over there and do all the work to get what I need out. But what happens is, so we get this sickle cell blood. Just because we have the blood, I need to be able to get out CD34 plus stem cells. There's a process, we add a bunch of chemicals, the blood separates. There's a little thin layer that I collect that has a CD34 plus. Now, the CD34 plus can grow into different things. You can get all these different types of cells. What I want is down here. See, at the end, it turns into a red blood cell with the right conditions. I don't want red blood cells. I want erythroblast, which starts here. And the reason why I want erythroblast is because, like they said in the papers, the HDAC inhibitors are increasing fetal hemoglobin. So we want to know, so like a perfect model would be fetal hemoglobin because it hasn't become sickle cell yet. So I'm collecting fetal hemoglobin from sickle cell patients before it becomes the actual sickle cell, which is crazy. This is what it looks like under a microscope. Looks weird, doesn't it? Like it does, like you would expect it to look like blood cells, but no, it don't. That's just, this is what it looks like. So so I have these primary cells. The number one thing about primary cells, and I didn't know this, nobody told me this till I got to that part of growing a cell, was that in order to be able to do our experiment, the trapping experiment that I talked about, is you have to be able to transfect cells with our flag tagged HDAC DNA, right? Well, what no one told me was that it is hard to transfect primary cells, almost impossible. And no one told me. So what I've been working on now is there are multiple types of transfection. There's transient transfection and stable transfection. And your transient transfection is what we do in our lab. We use a chemical agent called Jet Prime. And what that chemical agent does is that we have our DNA. We take this chemical agent pokes holes in a cell, sends our DNA into the cell, the DNA gets into the cytoplasm, cell splits, DNA gets into the nucleus just does a thing, split, creates DNA, creates protein, and so forth, DNA, RNA, protein. Sounds easy, right? Well, for primary cells, they don't really work that way. So when I did a chemical transfection of these cells, they all died. Like there were no cells left. Like you see this bunch of cells, when I went and looked at it again, no more cells. Like there was nothing there. Killed all of them. And that's what a chemical transfection. So then I tried another transfection method called electroporation, which is kind of like, yeah, it's a shot. So imagine a taser, but it's a taser for cells. We like to call it a tickle. It tickles the cells, the cell membrane opens up, the DNA gets in. Well, these cells are primary cells and they're sickle cell. They're cells from sickle cell patients. So they're kind of already kind of damaged cells. So doing electroporation, guess what happened? Fried them all, died. So there was one more transfection method that I'm using now, which is called nucleofection. And nucleofection, what it does is it is a mixture of electroporation and the Jet Prime with the chemical transfection. And what it does is that somehow it uses a less voltage to get your DNA into the cytoplasm. But then it also uses a chemical that gets the DNA into the nucleus as well. So you have your DNA inside both. So with that process, hopefully you can get it transfected because there's just so much DNA floating around. And you don't have to worry about, mitosis of splitting for the DNA to get to the nucleus because it's already in the nucleus and the cytoplasm. I actually got that to work. I got it to work. I don't have any pictures of it here, but I did get it to work. But now I'm just working on getting it to basically optimizing it so that I can get a lot of expression. But if that doesn't work, because in grad school, you got to have a plan A through F. If that doesn't work, which if you guys go to grad school, it's going to happen. Like grad school is all about it not working. And you just have to just keep going at it. Like nothing works, like nothing. And if it does work, it's a miracle. But 9 times out of 10, you're going to do something for a year. And at the end of that year, it's not going to work. And it just happens that way. So if I can't optimize the nucleofection, me and Dr. Foam sat down and we came up with an experiment called DIP, or double flag tag IP of HDAC1. So what happens is that we have to grow, we're going to grow these HEC293 cells. We know we can transfect these cells and grow our flag tag protein. So we're going to transfect a cell line called HEC293. Once we do that, we're going to IP out the flag tag DNA, right? Oh, the flag tag proteins. We're going to IP them out. So we have them on the bead, right? Then what we're going to do, where the second IP comes in, is that we're going to wash away, hopefully, we can wash away any type of substrate or protein that is involved with the HEC293 cell line. And on the bead, we should just have our mutant protein, right? It should just be the mutant protein on the bead. So then we're going to take that and we're going to add our erythroblast lysate. And we're going to add that to the beads that already have the mutant proteins on them. And then we're going to incubate that, and then we're going to run them on a jet. So I did that, and it didn't work. So, like I said, that's normal. It didn't work, because as you can see, this all looks the same. In a perfect world, these 3 lanes would have more bands, because we captured substrates that were involved with the erythroblast. This was the first time I ever did this experiment, and I did this experiment 3 days before my 4th year talk that Dr. Shute came to see. So I just had to put it up there. In the 4th year talk, it went by smooth. I was like, yeah, man, that's gonna work. Actually, I did get it to work, just not with erythroblast cells. I ended up using the HEC 293 cell line, but then I ended up using a, I think it's called a MBA 231. It's a triple negative breast cancer cell line, and I got it to work with that cell line. So now hopefully I can apply it to the erythroblast now, but I did get it to work. So my future direction is to be able to transfect the erythroblast, which I'm still doing, probing for the HDAC1, so being able to see that my HDAC1 is actually in the cell, which I've been able to do that now. And perform an HDAC1 trapping experiment. I'll be doing that actually next week, since I got everything to work. And taking that to MS or mass spectrometry proteomics experiments, so then we can discover those proteins. And if we discover those proteins, maybe one day a company or Dr. Flum, we can, because in our lab, we also create small molecules as well. Maybe there could be a small molecule created that can counteract those proteins. So, you know, people with sickle cell anemia can have a better lifestyle. So just a summary, I applied K-class to malaria. I applied K-class to malaria, and I tried to apply and still have applied HDAC1 trapping to sickle cell anemia. I have to thank these people in the lab. These are all my lab mates here. This is my PI, Dr. Flum. All the doctors, people here. Dr. Shute, you up there.
I appreciate that.
That's my primary investigator. These are the people on my committee. The guy that asked me, are the lights gonna give us cancer? That's that guy right there. That's Dr. Semmer, the guy I did mass spec from. And then this guy, Dr. Claudio Verani, is hilarious because he's an inorganic chemist. He knows nothing of biochem, nothing of mass spec. So he was just in our individual meeting, his hand was just up the whole time. I had to answer. I said, these people are the ones in this picture. Saw my funding, and you know, what I wish for you guys is, my advice is just stay focused. You know, school can get hard. There can be a lot of distractions that come in. Like I had distractions like football, family, like all the different types of stuff. Just stay focused. If you stay focused, it sucks, but you'll get to that. What do you need to do? Get good grades and be nice to your professors. I'm telling you. Dr. Shute thought this was weird when I came, but at Northern, with the football coach at Northern was like, every football player will sit in the front of the class, right in front of the desk. So if we had this room, I would be sitting right here in front of Dr. Shute.
And we were in Maine 22, he was for organic, came in and said, everybody else sat in the back. And Eric had the whole front table to himself.
In every class, I would sit right in the front. So even if you're doing bad, the teacher's like, man, this guy's really trying. And that's what you got to do, literally sit. You think it might not be a big deal, but like as someone who's taught, like I never want to teach again. Like be nice to your professors, man. They go through a lot. Like I remember my first day teaching, I'm sitting there and I'm just looking at the kids just looking back at me, just like mouth open, red eyes, on their phones, like just like you don't want to be here. So get good grades. If you got good grades, get into grad school is nothing. Like they look at your grades, they look at your letters of recommendation. Everything else, I'm telling you, they don't care about. Grades, letters of recommendation. Be nice to your teachers because they give you letters of recommendation. So if you sit in the front and you go ask for one, they're gonna say yes. If they don't know who you are and you're sitting in the back, probably gonna say no. So be nice.
Just add, we've all had people, Dr. Baylor, Dr. Coach, and I have all had people who have asked us for recommendation letters that we don't like. We don't answer the. I don't answer the emails.
Yeah,
I did a couple times. I won't answer emails. I'll respond to them because I can't give them a letter of recommendation.
But I can think of a few people right now.
Yeah, see, I'm telling you, it may seem like something like I know you want to be in the back or like be in the front. I'm telling you, sit in front of the class directly right in front of them, eye contact the whole time. I'm telling you, it pays off because like even when I was teaching, the students that did that, if they ask for help after, I would actually be like, all right, let me make some time. Cause like you care. Like, let me make some time. So like I would make like office hour time specifically for them. Like, hey, send me an email, I'll help. I'm telling you, it will pay off. When you need letters of recommendation, it will pay off. I'm telling you. What you really shouldn't do, settle for less. Always try to be above average. Always try to be above average. I'm telling you, like if you put the extra effort in that everybody else isn't, you're gonna stand out. Like you really are. Like that's what I always try to do. Like in Dr. Schutz's class, if the average was a C, I'm trying to get an A+. Like I'm always trying to shoot higher. And like I said, teachers see that stuff. Like y'all might think they're just like going through when they got 100 people. No, they see the person that's actually trying. So if you show an effort, they're gonna see it.
Yeah,
And that's it.
the student I like who is trying, even if they can't make it, I can help them if they want. I mean, it shows us that you are willing to go, a step further to improve yourself. And we are there for everybody, but those who try more, we help them more because we can see they're trying. And there are some who do nothing.
It is. I was a football player. I remember I had a couple classes with them, and they were all sitting in the back. And we were all sitting in the back in a group. And I'm like, yeah, no, I can't do this. Like, you know what to put me in that group. Then they all think you cheating because we sit next to each other. It's like, come on, man. We got to get this together. So I would literally sit right smack dab in front of every class, right in front of the teacher.
I had a class, an evening class, where I had this football group would come in late every day, 20 minutes late. So I finally locked the door and cut them out. So the next day, the coach came to see me. And I told them they don't come on time.
Yeah,
they said they should be. They don't need to, they usually have to go shower and eat and all that. So you know you sign up for this class. You should be here on time.
Yeah, that's another thing too. Always be on time. You know, I would always, it was a couple times that wouldn't I show up like 30 minutes early? He'd be like, why are you here?
We got organic at 8 o'clock in the morning. For 4 years straight, I think I had organic at 8 o'clock in the morning. We got to put them all on the same day. So we had organic at 8 o'clock. And Eric was always there. And main 22. Or be the second or third floor.
It was the third floor. It was the third floor. Like I would beat the janitor people there for them to unlock the doors. So I'll be sitting out there making sure, all right, let me be early, have my Tiffin foot. No, you wanna know what's funny? Was when he didn't know that I was a football player the first month, even though all I wore was Tiffin football gear.
I didn't expect the Tiffin football player to be an organic.
Well, but then, so Fridays, if we traveled, like, I wouldn't be there. He never noticed. And then he started giving my grades back. I even had you sign the slip and everything. Then he was giving them grades back one day. And I remember Dr. Shoup was like, Eric, you play football? I was like, yeah. And he was like, really? You play football? And he was like, I've never had a football player take my class before. And I was like, oh, all right.
We only had one since. Mason was the center from 2016, 2017 around there.
Yeah, I remember that guy.
I remember Mason. I don't want to get off track, but I don't expect you guys to ask questions about his research because it's like crazy, tremendous stuff. But any questions for Eric about anything else? Unless I have to go and Dr. Bailey, if you got questions about the research, I'm fine with it.
I want to see what he finds. I already asked the first question, why he's doing it, because I had suspected that you or somebody in your family or somebody you knew had that. So concern.
Yep. I'm a carrier. My mom's a carrier. One of my sisters is a carrier. And my mom always makes jokes where she's like, well, if malaria ever breaks out, we know who's surviving. And I was like, why you can't make that joke about other kids?
I have a question. The chloroquine, is it the same chloroquine they were using for COVID?
I'm glad you brought that up. And that's why usually I don't have my opinions on this type of stuff, or I keep them to myself. But I have no clue why they were using chloroquine, something for a parasite, on a virus. Even for people who don't know science,
yeah,
virus, parasite. how did those, like, when I first seen that, I seen it on Facebook when I first seen it. So I'm like, this isn't real. Like, I'm actually doing real research. Like, nah, they would, like, I'm not seeing it on any journal or like anything like that. I'm just like, what's going on here? And then I'm like, why does that sound familiar? I'm like, why do they keep saying chloroquine? They're talking about chloroquine. And then I was actually doing that proteomics, and it dawned on me that I'm like, they are talking about the same chloroquine for malaria. No clue. No clue. I was like, let me even research this, because Google is a good tool. It's a good tool, but don't believe what's on Google. Like use it first, then go to I don't even
people like them on their research paper not to go there and get
yeah, like oh,
all right. Conversation.
Yes, it's good. Okay, so like for an example, like let's say you guys want to come to Wayne State and get a PhD in chemistry. Your second year, you have something called your orals. And your orals is you have to come up with a prospectus. So what are you going to be doing for the next 4, 5 years? Then you have your proposal, an independent proposal. The proposal has to be in the, so like I was analytical, my proposal had to be in something that wasn't analytical, and I couldn't do mass spectrometry. So I chose to do inorganic organic chemistry. I'm horrible at inorganic chemistry. So I decided, I get on Google and I'm just like, what's a environmental problem going on? The first thing Google popped up was meth gators. Because people in Florida were flushing meth down the toilet. The alligators were eating the meth, or it was in the water. And then the alligators were attacking random people and random things. That's what my independent proposal was on, was creating a molecular imprinted polymer to test for meth in water and waterways in Florida so that we can prevent meth gators. That was Google. And the moral of the story is, like, did my independent proposal get ripped to shreds? Because the point of your orals is they want to put you up front and they want you to speak and they want you to represent everything with science. Why do we care about meth gators? Okay, so you're using molecular imprinted polymers. How do you make that polymer? What is that polymer going to do? Is that polymer going to bind to meth, just to methamphetamines, or is it going to bind to anything that's in the water? And then they want you to explain everything with science. Now, did they rip me to shreds for an hour and 25 minutes? Yes, but I was able to actually defend my proposal, but I got my proposal from Google of meth gators. Don't, so Google's cool, but try to use something like we use, like, I don't know if Tiffin has it, but like through Wayne State, we can get something like Web of Science. And it's like just all peer-reviewed articles. Sometimes Google Scholar will give you, will let you have access to certain scholarly articles, but even Google Scholar, you gotta be careful.
And the number one thing, I mean, but I got to go to, I wanted you to get for this as well, as Dr. Baylor has said, when we had our general science degree, we never had a graduate doing this kind of research. We always put them in general science because we had no place else for them.
Yeah.
In most cases. And I think what happened, and you went beyond the chemistry courses that you needed to take for your general science degree. Because the general science degree had, I think, maybe 4 bios and 4 chems, maybe, or 2 bios and 2 chems. Anyway, he went beyond, and that was what I think kept him going in the grad school, because he had instrumental, that instrumentation. He had organic, he had biochem, so he had all those building blocks together that gave you confidence in it. And that's why I think he's excelled. So it's rare to have a general science graduate from TU going to grad school with that kind of research.
Because now in genetics, they learn all this acetylation, deacetylation, and then in cell monomers, study about kinases, and we use the biotintylated strep targeting for cell blocks when we do it in that class. So we'll handle many of these things.
Oh yeah, they have southern, western, eastern, southwestern blocks. There's a bunch of it. You learn all of it. I mean, You know, like if you plan on going to grad school, like really focus in on that stuff. Because, you know, one thing that helped me was like, here, I never touched an instrument. The only thing I ever had was the schematics to put up. And Dr. Shoup teaching us, this is what the instrument does, this is what it looks like, this is this, this, and that. So when I got to Wayne State, I never had the physical to be able to touch it, but I already knew what I was doing. So when I got in, and you can ask Dr. Shoup, he came to visit, I'm inside of a mass spec, pulling it apart to take parts from another one and putting them together. And while I'm doing that, I can also explain what each part is, what it does, you know, what this electron multiplier does. What does this ESI source or electron ionization source, what it does? You know, just every single piece I could put together. And my PI at the time, Sarah Trippin, like, was just like, I went to, like, she came down here. She's like, I went to the school. She came and visited here. And she was like, this where you did chemistry? Like when we was driving in, she was like, where are we? Like,
we had to speak to the class organic. We had at St. Mary's, and I was embarrassed as we were at St. Mary's. Yeah. When you bring this person from Wayne State into, you know,
yeah, she and my first PI was, so there's something called the Beeman Medal. Yeah, she was the Beeman Medal winner, like that year, because this was it my first year there, or was it my
2018, 2017?
Yeah, it was. Yeah, it was before COVID, so she came down. And basically, the Beeman Medal in mass spectrometry is just one level below getting the Nobel Prize. So she was like, like up here, and then she's like, she was like, it's schools like this in America, because she's German, and she's like, it's schools like this in America, and she's like, you did chemistry here? I was like, yeah, right in that building right there. We came over, we looked at the building, and she's just looking, and she's like, But in the car, she was like, on our way back, she was like, you did chemistry at this place? And you learned, she's like, you learned mass spectrometry with no mass spectrometer? I was like, yeah.
I think what she really meant was they teach chemistry at this place.
Yeah, because I think, because didn't this building used to be like some fabrication, like, it was like somewhere.
Yeah.
And she was like, what's that building? I was like, I think they make carpet there. So it was like, you know, all the lessons I learned here really helped me when I got into grad school. And, you know, not having all those things really helped as well, because, you know, like I could do stuff that like they really couldn't do, or like I had to learn a part that they maybe have known a little theory, but I had to know the theory because that's all I ever had to learn was the theory. And then Dr. Shoup would show us schematics on how it like goes together. So I kind of knew it, I had just never physically done it. So, you know, that kind of gave me a head up. And then with Dr. Shoup, since we didn't have all of that big fancy stuff, we really had to learn everything about it. So when I got there, you know, I told you when you first get there, you have to take kind of like the ACS exams of all the 5 disciplines. Most people only get 1. I got 3. And that's because of how in-depth we did with the analytical chemistry, with the organic chemistry, with the biochemistry, and then like the classrooms were small. How many of us were in the classroom?
We had about 15.
So 15 in the classroom compared to Wayne State where it's 300. So having that small classroom and being able to be like, hey, Dr. Shoup, I need this help, or calling Dr. Shoup, like you can't call your teachers at Wayne State, but being able to call Dr. Shoup and be like, hey, I'm stuck on this organic problem. Just that intimacy of only it being 15 people like really helped out a lot as well.
One more thing, we were doing the research on maggots and the flies, and now you guys know why he didn't shy away from that. Because looking at proteins of 25,000 AUs versus a maggot, even I thought before I heard his 4th year talk, I asked him that question because I don't think they ever do it, and he says, "Oh yeah, I'll do this, this, this." I'm like, "Are you sure?" And then I go in to hear him talk. I'm like, oh yeah, of course he knows why. If they can do all that stuff, what's a maggot and a fly? It's nothing.
Yeah, the only thing, so when being able to do that was taking it from the maggot, I guess the big question is, and Dr. Shoup proposed this question, was that when that maggot goes through metamorphosis, will that drug not be seen in the fly? Well, we don't know. So what you could possibly do is the only thing about analyzing something like a maggot is that it's a maggot. It has skin. It has all that. Just squish a maggot and you'll see. You don't want to put that into your mass spectrometer. So what you would have to do is what we call a lot of sample prep. So it would have to be a lot of pre-separation before we would even get it into the mass spectrometer, because that stuff that you guys have done, LC, it'll clog up your LC instrument. And like nobody in their right mind would put a whole maggot into an LC instrument. But what you can do is because no one would do that, and it's a maggot. So like just all that skin and all that other debris, like it could possibly, when running it through a mass spec could, if you don't have the right instrument, your analyte could possibly be masked by other analytes that's within the maggot. Because it's like, if you're looking at, you guys are looking at it forensics. If you find a body somewhere out in the woods and there's maggots growing in it, I mean, you don't know how long that body has been there. You don't know if any other animals have came, what their anything. So, when he proposed it to me, I'm like, yeah, that's pretty easy. You would just, the only hard part would just be, if we get the maggot, obviously grind it up. Then it would have to be some type of separation within the maggot. The only separation I feel like you would need is, like I said, we need to get the skin, we need to get the goop away. So a simple solid phase extraction, probably, give it 2-3 times to a solid phase, some type of solid phase extraction, could get rid of all that stuff. Then once I get that, with using this maggot and it being a, complex organism, and depending on where it was growing, we need some separation. So normally you do the LCS separation, and that's normally what's used in proteomics. But with the maggot, if we don't want to do LC, there's another type of separation. People argue in the mass spec world, is it a separation or is it actually an actual mass spectrometer analysis? Some people say it's both. Some people consider mass spec just a separation. But there's something called ion mobility, where what ion mobility does is you have your analyte, and your analyte is traveling through an inert gas. So it's coming this way and the gas is coming that way. And the faster the analyte will travel through the gas is if it's more compacted. So if I have my keys here and my keys are flying like this, it's flying through the gas, it's going to be interacting with the gas, so it's going to move slow, right? But if it's compacted and it's flowing through the gas, it's going to go faster. So what you can theoretically do is you could have the LC separation. And then when you still have analytes within that sample that are still not separated from each other, or isomers, you could have the LC separation. Then in theory, you could have the ion mobility separation. So now you have 2 separations. So now you're separating isoforms, then separating isoforms again. Now when you hit the mass spec, I can now see everything now. And if you use a high mass resolution mass spectrometer, something like an Orbitrap or a TOF, or just even a TOF, with those 2 levels of separation, you should be able to see everything. Your drug, and then if you also want to learn, I guess, me being a proteomics person, if I want to learn about the other proteins that's in the maggots, because how did that small molecule affect the maggot, and then will it eventually transfer into the fly? I could learn about what happens with the other proteins as well. Yep.
Could your mass specs, would they be sensitive enough to pick up different isotopes? Like if we got his drugs labeled with like 15N.
Oh yeah, that's
be able to tell the 15N of the same protein from the 14N of the same protein.
Oh yeah, that's super. So we can get down to the octomole.
Oh, okay.
That's simple. Yeah, that's real easy. Yeah, octomole. Yeah, we can get down to so parts per million, parts per billion, that's easy. We can get all the way. We can definitely get down. And then like what was funny was actually last week when I was talking to Dr. Shute, I was actually at a mass spec. So there's a mass spec company called Bucher. And what they do is when you're a mass spectrometrist or are in someone's lab, they want to sell you a mass spec. So they so they always throw like these big like shindigs where like they have like coffee and alcohol and like this is that, and then like they have speakers come because they're trying to sell you an instrument. So like I forgot to bring my hat, but they give you like hats and mugs and like all this stuff. And the instrument that they're trying to sell is actually an ion mobility combined with an ion trap combined with a TOF, or time of flight instrument. And I was like, that would be the perfect instrument that Dr. Shoup would want to use. So I sent him a picture like, hey, I'm at this conference, look, and it's the instrument right there. That would be perfect for what he wanted to do.
Are you buying it?
You could probably get one at Tiffany. Hey, if this thing worked, you could get that instrument at Tiffany.
We'd have to have someone who knows how to run that type of analysis.
They come to demonstrate and then you have to.
Yeah, they'll send somebody out. They'll teach whoever how to do it. Like that, you just
on the big one across the Detroit River in Windsor, the one that they have at the Great Lakes Research Center.
Oh, you do?
On the other side.
Okay.
What we're trying to do is also have Wayne State create a mass spec camp.
Oh yeah, so we got that. That's probably going to be a go. So at that same conference that I was at, it was at U of M. So the mass spec room that he's talking about. So if you ever want to do mass spec at Wayne State and not go there, you come to we call it LIC, or the Lumagen Center. And it's ran by a lady named Dr. Judy Westrick. And she's like a mass spec guru. And we have 17 mass specs. We have triple quads, single quads. We have ICP-MS, which is basically you have a sample and you shoot it with a thunderbolt. So like when you look at it, it's literally you see purple lightning in this tube and it's hitting your sample and frying it. We have that. We have a multi-TOF. We have like 2-3 different types of Orbitraps. We have just any type of mass spec instrument you can think of. We have it along with chromatography. So, Dr. Shoup came and seen it. And I remember the first thing he said to me was, he was like, do all those work or are they just sitting there?
I thought about the spare part people, They had them sitting there like usable parts.
Well, that's just the mass spec. We also have like 3 NMRs. We have X-ray crystallography. We have some topography machines where they like look at the surface of monolayers and it like that. We got like 4 of those. But Judy Westrick, I was at that conference and I was like, hey, my undergrad professor, Dr. Shoup, he wants to do a mass spec camp. We have a bunch of mass specs, have them come in. She's like, oh yeah, I would love to do that. She was like, it could, I might not, or I might, but I might also have grant money for it as well. So to have like, the camp could be like, like a real camp, like people come for a week, put them up in the dorms. Then all they do is literally for 2 weeks, just mass spec analysis, learn everything about the mass spec.
I think it'd be phenomenal to do that. I think it's a great experience to have our undergraduates do that. To have that kind of, because I've seen what they've got available there, and Eric would be running it. That's my vision. Yeah. Okay, I don't want to teach you. We got to head over, get some lunch real quick. So let's thank Dr. Davis one more time, please. Where? Okay.
Do you want me to hit stop on this?
Yeah.
Nice to meet you.
All right, nice to meet you.
We're gonna head across the street.
To where?
Wall Street.
Okay.
And they're gonna join us.
Okay.
I'll have a couple ideas for you after I find a couple more articles.